Dear students, so in previous class we were discussing about the divisibility. Now in this class let us discuss about the greatest common divisor. So what is a common divisor? If A and B are any two integers, if A and B are any two integers, and if D divides both of this A and B, D divides A and D divides B, then D is called the common divisor of A and B. One is a common divisor of every pair of elements. Now, if A and B has a common divisor D, then D can be expressed as a linear combination of this A and B. That's an important result. If D be the common divisor of A and B, that is if D divides A and D divides B, then D can be expressed as a linear combination of this A and B, means there exists some x, y following set, x and y are integers such that D equals Ax plus By. So this can be proved by induction hypothesis. First we assume A and B are greater than, they are non-negative integers. A and B greater than or equal to 0. They are non-negative integers. So when n put n equals 0, choose an integer n, or to say assume A and B, then choose n such that n equals A plus B. A and B are positive integers, non-negative integers. Choose n such that n equals A plus B. Now, if n equals 0, what happens here? If n equals 0, then we have n equals 0 means A plus B equals 0. A plus B equals 0. Why? Because we choose n equals A plus B. Since A and B are greater than or equal to 0, A plus B equals 0 should imply A equals 0 and B equals 0. This is the only one possibility. A equals 0 and B equals 0. So here what is D? D equals Ax plus By. That's our requirement. Put n equals A plus B. If n equals 0, since A and B are non-negative integers, then A plus B equals 0 should imply A equals 0 and B equals 0. So take up this D equals 0 as x equals 0 and D equals 0 with x equals 0 and y equals 0. That means this result is true for n equals 0. Now for induction, we can assume that the result is true for 0, 1, 2, 3, etc. up to n minus 1. This is our assumption. Assume the result is true for 0, 1, 2, 3, etc. up to n minus 1. Now suppose A greater than or equals B. A greater than or equals B. This is only for our convenience. If B equals 0, what happens? If B equals 0, then we have D equals Ax plus By. If B equals 0, then take a D equals A with x equals 1 and y equals 0. Then again this linear combination is possible there. If B equals 0, D equals x plus By become D equals A with x equals 1 and y equals 0. Again the linear combination is present there. Okay. Now if B greater than or equals 1, suppose B greater than or equals 1, then this result, you can apply this result for this, you can apply this result to this A minus B and B itself. Why? Because what is A? B is A minus B plus B. Okay, that equals A plus B minus B. What is A plus B? We can choose A plus B as n, so it is n minus B. But what is B? B greater than or equals 1, so this n minus B less than or equals n minus 1. N minus B less than or equals n minus 1. And what is our assumption? The result is true for n equals 0, 1, 2, 3, etc. up to n minus 1. Okay. So you can apply this result to this a minus b and b. Agreed. Why? Because this a is less than or equals n minus 1 and we assume this result is true for n minus 1. So you can apply this result. Hence by induction there exists there exists d following such that this d divides a minus b and d divides b. Okay, d divides a minus b and d divides b is of the form d equals since it is true for n minus 1, so it is d equals a minus b into x plus by. That equals ax plus b into x minus y. It is ax minus bx plus by, so it is ax plus b into y minus x. Okay, that means d equals ax plus b into y minus x means this d equals ax plus b into x plus b into y minus x means d divides this ax plus b into y minus x also. Agreed. Moreover, this d divides a minus b and d divides b, then by the property of divisibility, d divides this a minus b plus b means a, that implies d divides a. Agreed. Thus we have d divides a and d divides b, and hence d divides ax plus b into y minus x. Listen, hence we have finally d divides a and d divides b, and also d divides ax plus b into y minus x. That means if d divides a and d divides b, then d can be expressed as a linear combination of this a and b. Okay. So when a and b greater than or equal to 0, then the result is proved by using this induction. Clear? Now suppose a and b are negative, what happens here? There is another possibility. They are also integers. A and b are negative. Then this result is true for its modulus. That is, take d equals mod ax plus mod by. Since a is negative, what is mod a? Mod a equals minus a. Also, since b is negative, what is mod b? Mod b is minus b. Okay, therefore, this can be rewritten as d equals minus ax plus minus by. That means d equals a into minus x plus b into minus y. Again, d can be expressed as a linear combination of a and b. Since x and y are integers, minus x and minus y are also integers. Okay. So here when a and b are greater than or equal to 0, then this if d divides a and d divides b, d can be expressed as a linear combination of a and b. Also from here we prove this result also when a and b are negative, d is as a linear combination of this a and b. D is a minus x plus b into minus y. Okay. So this is the common divisor, and this is an important result regarding this common divisor. If d divides both a and b, then d is the common divisor. Then that d can be expressed as a linear combination of that a and b itself. Agreed. Moreover, if d divides a and d divides b, or d be the common divisor of a and b, then every common divisor of a and b divides this d also. How? Let d and d be the, or d divides a and d divides b. Let d divides a and d divides b. Then d can be expressed as a linear combination of this a and b. Now, if another element, if d1 divides a and d1 divides b, then we can show that this d1 divides this d itself. How? When d equals ax plus b and d1 divides a and d1 divides b, then clearly this d1 divides ax and d1 divides by. Okay, that means this d1 divides this ax plus by the divisibility, that is d1 divides d. Means if d be the common divisor of a and b, That is, if D divides A and D divides B, then every common divisor of this A and B must divide this D also. Clear? Now, let A and B are any two integers. A and B are any two integers. Then there is one and only one number D. There exists one and only one number D, means the uniqueness of D is strictly preserved there, having the following property, having the properties. First one, the non-negative property, D greater than or equals 0. And the second one, D divides A and D divides B. D divides A and D divides B means D be the common divisor of A and B. Also, if E divides A and E divides B, then this E divides D. Why? Means if D be the common divisor of A and B means D divides both A and B itself. Also, we already proved that if D be the common divisor of A and B, and then we show that by the previous argument, we can show that every common or every divisor of this A and B must divide this D itself. So here, according to our hypothesis, if D divides A and D divides B means D be the common divisor of A and B. Moreover, if E divides both A and B, E is another divisor of A and B, then by the previous arguments we can conclude that this E must divide D itself. Okay. D also greater than or equals 0. Now, how to prove the uniqueness here? Uniqueness means, if possible, D dash also divides. If D dash satisfies both of these conditions. That is, if D dash, suppose D dash be another divisor, means D dash divides A and D dash satisfies these two conditions. That is, if D dash divides A, comma D dash divides B, and D dash divides D dash divides A and D dash divides B. If E divides A and E divides B, then E divides D dash also. Okay. So D dash satisfies these two conditions means clearly D dash divides D. D dash divides D means we have mod D dash less than or equals mod D. Why? Because we see this result. We obtain this result, or we already proved this result. When n divides D, then mod n less than equals mod D. Okay. So when D dash divides D, then mod D dash less than equals mod D. Similarly, if D divides D dash, that means mod D less than or equals mod D dash combines these two results, then mod D equals mod D dash. So the uniqueness of D is preserved. Okay. So why D dash means why? Because this divides D equals D dash. Why? Because D greater than or equals 0. D greater than or equals 0, and as our choice, D dash also greater than or equals 0. So mod D equals mod D dash should imply D equals D dash, hence the uniqueness is preserved. Okay. So we can say that our conclusion is, if D be the common divisor of A and B, then this D greater than or equals 0, then there exists only one such D, and which satisfies the conditions D divides A and D divides B, then, and if E divides A and D divides B, then that E divides D itself. The proof is in this way. These are immediate, and for uniqueness, if D dash satisfies these two conditions, means D dash divides D, D dash divides D means mod D dash less than equals mod D. Again, if D divides D dash, mod D less than equals mod D dash. So we have combined these two results, we have mod D equals mod D dash. But since D and D dash are greater than or equals 0, then D equals D dash. Okay. So these are the properties regarding the common divisor. Okay. Then, if D greater than or equals 0, suppose D is any integer which satisfies these properties. For any two integers A and B, D greater than or equals 0, D divides A and D divides B. If E divides A and D divides B, then E divides this D. Such a D is called the greatest common divisor. So this can be rewritten as D equals greatest common divisor. This is read it as the greatest common divisor of A and B. Agreed. So, if D be the greatest common divisor of A and B, then the D can be expressed as a linear combination of both of this A and B. Agreed.